The last lecture of Physics 72 discusses diffraction. Simply put, diffraction is the bending of light around obstacles. This bending of light leads to patterns of dark and bright fringes similar to interference, but the two phenomena have their own distinctions. We explore the differences in this lecture, which is based on Chapter 36 of University Physics. Here are the objectives for this lecture. You may pause the video to have a look at them. This picture shows a green laser passing through a small opening, or an aperture. If light was considered only as a particle, we should only expect one bright spot, as the laser marks a single spot when hitting any object without any obstacles. The presence of the diffracting screen allows for light to shine through multiple spots, and upon looking at the spots closely, we see fringe patterns that should be familiar to you from interference. We explore how these patterns come to be for this lecture. Now, before we begin, let's try to understand a simplified setup for our diffraction examples. We have parallel monochromatic light rays hitting a screen with a slit of width A, so the light's coming from the left. If we treat light as if it were mere particles, and the light rays only signifying the trajectories of these particles, geometric optics tell us that light will take on the shape of the slit when shown on another viewing screen, as the one seen on the right. But the thing is, this isn't what is observed when an experiment is done. This picture shows a viewing screen where light from a red laser just passed through a barber's razor blade. If we treat light as a particle, then the red background should have a sharp color, or a sharp shadow. Instead of the expected result, we get patterns of alternating dark and bright fringes. This strengthens the argument that light has wave-like properties and that some form of interference is at play. We call this pattern, or the one that we saw in the previous slide, a diffraction pattern, and it is similar to a set of interference fringes. But then, interference occurs only when there are two or more sources of light waves. Where do we find the other source of light if our example only has one source? To briefly answer this question, let's zoom in on the opening slit, or the aperture. While this wasn't emphasized in the lecture of light wave propagation, Huygens' principle states that each point of a wavefront can act as a source of wavelets, or mini-waves. This principle helps the derivation of the laws of reflection and refraction, but we really didn't discuss this in the earlier lectures. In any case, when light hits the aperture, we can take every point along the slit as sources of waves. These waves would then be responsible for producing the diffraction pattern. We can then take diffraction to be interference effects due to the superposition of multiple light wavelets from the aperture. Because point sources produce circular wavefronts, we expect the light waves to deviate from the straight path upon hitting the aperture. In simple terms, diffraction can be considered as the bending of light around obstacles. Recall from our earlier diagram of light passing through a narrow slit. Since we consider light to behave like a wave, we expect it to deviate from its originally straight path, which is why we see its shadow to be not as sharp. Another way of imagining the wave-like property of bending around corners is when the sound comes from a small opening. When it is loud enough, we expect to still hear the sound even though the opening is not directed straight towards us. This is the reason why we can hear cars coming from an alley even though the cars aren't approaching us. Before we digress too much though, take note that the fringes in diffraction patterns result in the superposition of light wavelets. Because of this, we consider that diffraction is an interference effect. The first part of the lecture discusses two types of diffraction. They are classified according to the relative positions of the light source, the slit, as well as the viewing screen. The two types of diffraction were extensively explored by a lot of scientists in the 1800s that names have been given to each one. Augustin Fresnel was a French physicist who was one of the proponents of the wave theory of light. Near-field diffraction is named after him. In this type of diffraction, the point source and the screen are relatively close to the obstacle. The intensity of the near-field diffraction graph seen on the top right can look a bit complicated. And this is owed to the fact that if the light source and the screen are close to the obstacle, light rays may not be considered as parallel. So from what you remember in the previous examples or in the previous lectures, we always had to make sure that the light rays incoming certain boundaries had to be parallel to simplify our calculations. So if we have angle dependence with these light rays, it can make the geometries of the rays a bit complicated to analyze. And the diffraction patterns actually kind of look complicated. One way to make understanding of diffraction easier is to place the point source and the screen far enough so that the light rays entering and exiting the screen can be approximated as parallel to each other. This is true for far-field diffraction or Fraunhofer diffraction, which is named after Bavarian physicist Joseph von Fraunhofer. He invented the spectroscope, developed diffraction gratings, and is popular for the development of the extensive study of diffraction today. As stated a while ago, the point source, screen, and obstacle should be far from each other for Fraunhofer diffraction, and this leads to the light rays being parallel to and from the obstacle. Physics 72 will focus on the elementary discussion of far-field diffraction. The diffraction patterns produced will always be dependent on the shape of the opening. In this example, for rectangular apertures, we expect the fringes to appear like crosshairs. Circular apertures, on the other hand, produce a ripple-like pattern on the viewing screen. The next section of the lecture looks deeper into the diffraction produced by a single slit. The example used to introduce diffraction a while back is an example of single slit diffraction, because the obstacle is made of a single opening with its width measured by A. Looking closely at the diffraction pattern, notice that the middle bright fringe has a different thickness with respect to the other ones. This already distinguishes it from the interference patterns produced from two slits in the previous lessons, namely because we expect the fringes to have the same widths. To understand how these patterns form, we can try to specifically locate where these fringes will form in the screen based on what we know from interference. Let's find an expression pinpointing where the dark fringes will form. From Huygens' principle, all points on the wavefront parallel to the slit can act as sources of wavelets. Let's keep it simple and choose two sources of the wavelets, one at the top of the slit and another at its midpoint. Let's choose P to be our point of interest, or where the dark fringe will be. The two sources we specified will have beams hitting P that have a path difference. From the geometry of the system, as well as similar derivations from interference a few lectures back, we take the path difference to be A over 2 sine theta, where theta is the angle in between the bottom ray and the horizontal axis. So you can pause the video if you want to understand it better. If you want P to be the location of the dark fringe, then we can equate the path difference delta R to half a wavelength. So both waves will destructively interfere. Remember that at the start, both of them should be in phase. After isolating sine theta, we can generalize our result by adding a plus and minus sign. This plus minus sign just tells us that a symmetric dark fringe can be seen below the horizontal axis. So we can have a sign result that's actually negative. It just indicates a dark fringe that's below point O. Now we have expressions for locating the two dark fringes closest to the center. What we determined so far are just two dark fringes. But then diffraction patterns have multiple dark fringes that spread out further from the center. How do we find expressions that help locate them? Recall that we derived the expression for the fringe location based on the assumption that our two wave sources were at the top and the midpoint of the slit, as per Huygens' principle. Then by the same principle, I can split the slit into 4 parts instead of 2, so quarters. Then I'll have two sources at distances a over 4 lengths apart. So this gives me sine theta is equal to 2 lambda over a, which is different from our first result by a factor of 2. From this, we can locate our second set of dark fringes. Again, I can split the slit symmetrically by dividing it by 6 instead of quarters, and this would give me sine theta is equal to 3 lambda over A. From this we get our third set of dark fringes. Now I can keep doing this. Instead of 6, I can divide it by 8, and it would give me expressions for the fourth set, and so on and so forth. What is important is I split the slit symmetrically in finding pairs of wavelet sources. We can locate the dark fringes based on how far they are from the pattern's brightest spot at the center, or we call it the central maxima. We'll call this y, the distance. The closest dark fringe may be described based on the angle θ1, or theta m equals 1. As we figured out the process on the previous slide, we can then find that the general expression for finding the mth dark fringe of the pattern is sine theta sub m is equal to m lambda over A. Lambda is the wavelength of the light shown, A is the width of the slit, theta sub m is the angular position, and m would be any integer that refers to the mth fringe. But then what we've had so far is an expression of theta, not really y. If we were to locate the dark fringes using position y, or its distance from the center, we haven't really done so with the previous equation. To fix this, recall that we're dealing with far-field diffraction. This means that angles theta are tiny enough to give us license to use the small angle approximation, where we can approximate sine theta to theta, and then theta to tangent theta. Sine theta sub m can then be approximated to y sub m over x, x being the distance of the obstacle in the viewing screen. And then we can isolate y sub m to have an expression for the vertical position of the mth fringe, or mth dark fringe, given by y sub m is equal to x m lambda over A. This slide paints a clearer picture of how the plane waves emanating from the laser turn to circular wavefronts upon passing through the tiny aperture. The first dark fringes are closest to the center, followed by the second set of fringes, then the third, and so on. We find these locations by just substituting the appropriate values of m to the equation. And then if you look at the formula, we can assert that the dark fringes should be evenly spaced apart, as they just differ by multiples of x lambda over A. This is true, with a notable exception in the middle spacing, since the first set of dark fringes are separated by a longer distance, as you can see in the picture on the top right. To deepen our understanding of fringe locations in these patterns, we then look for an expression for the thickness of this bright fringe at the center. To find width W of the central maximum, we observe that it is sandwiched between the first set of dark fringes. This makes things easy because all we need to do then is subtract y1 with negative y1 to find this width, because it's the distance. This gives us W is equal to 2x lambda over A, and tada! We have the width of the central maximum. With this, we complete the first objective in determining locations of dark fringes and the width of the central maximum. This objective serves to give us a better understanding of how these patterns look like based on experimental parameters such as the wavelength, lambda, the distance between obstacle and its screen x, as well as the slit width A. Looking at the equation for W, we can comment on how experimental parameters affect this width. Increasing the distance between obstacle and screen magnifies W. Choosing a color closer to red in the visible light spectrum also increases width. Finally, narrowing the slit also increases the width. You can try these out in elementary physics laboratories as well as the experiments. So let's try to answer a simple problem. You pass a 633 nanometer laser through a narrow slit and observe the diffraction pattern on a screen 6 meters away. The distance on the screen between the centers of the first minima on either side of the central bright fringe is 32 millimeters. So we're asked to find how wide is the slit, or the slit width. In answering how wide the slit should be, we recognize that the distance between the first set of dark fringes is just the width of the central maximum from a while ago. Isolating A from the expression and substituting the given values gives us the slit width as 0.24 millimeters. Now we move on to the last section of the lecture. It turns out that diffraction can also form from multiple slits. So for this part, we try to investigate that phenomenon and see how they differ from what we've discussed so far. We've already seen the intensity plots of single-slit diffraction patterns. I'll go ahead and spoil what happens when we choose two slits. If we choose two slits that are very narrow in width, this just leads us to a sinusoidal intensity plot with equal peaks for each bright fringe. If this seems familiar to you, your hunch is right, because this is just the intensity plot of an interference pattern a la Young's double slit experiment. What happens if we stretch the widths of the slits apart? So instead of them being narrow, they're slightly wider, that their width would be finite. We end up with the usual intensity plot for the interference pattern, but with the extra kick of the peaks being modulated by some envelope. This envelope looks eerily similar to the intensity pattern of the single slit diffraction setup. This should intrigue you because for two slits of finite width, we have a combination of the first two setups. And because of this, we complete the second objective of differentiating these setups based on their intensity plots. So the two slits of finite width is actually a combination of diffraction and interference. Now, while this may seem like I cheated, you don't have to worry. We will focus more on the trends of the equations rather than its derivation. While the derivation may be found in the book, it's not part of our objective for the lecture. We can leave it for a different video. Like the previous slide, I'll jump straight to the result. The general expression for the intensity pattern for two-slit diffraction given finite slit widths is given by I is equal to I naught cosine squared phi over 2 times the square of sine beta over 2 over beta over 2. We have two phase differences to consider, phi and a new one, beta. Notice that the first two factors of the intensity pattern, I naught and cosine squared phi over 2, are already familiar to us. This is the intensity for interference of the two slits. If you still remember, phi is the phase difference between the waves coming out of the two slits. To understand where beta comes from, let's focus on the one slit for now, instead of the two of them. Huygens' principle allows us to consider points in the wavefronts as sources of similar wavelets. Now, consider those wavelets on the slit there. While we skip the derivation, beta is the phase difference between the top and the bottom wavelet of the slit. To give a better intuition for the equation, we show the diffraction pattern for the two-slit finite width example. The periodic fringes are due to the cosine squared phi term, or the interference term, while the envelope that modulates the peaks are due to the square of sine beta over 2 over beta over 2, or the diffraction part. Remember that A is the slit width and D is the distance between the slits. For this example, D is exactly 4 times the slit width. This viewing screen obtained from an actual experiment zooms in on the central maximum, and we can see that inside the central maximum are fringes, 7 to be exact. Diffraction and interference are both in action at the same time. Remember that our example had D equals 4A. It turns out that if the distance between slits is a multiple of the slit width, or if D over A is a whole number, we have an expression that counts the number of fringes inside the central maximum. The number of fringes would then be equal to 2 times D over A minus 1. For D equals 4A, we should have 7 fringes within the central maximum. You can check in the intensity plot, or count the fringes in the experimental data, and indeed see that we have 7 fringes within the central maximum. This slide shows a simplified diagram of how the two-slit finite slit width setup produces its intensity pattern. An experimental result may be seen on the top right part of the slide, and you can see that you do have the central maximum being divided by fringes. It's interesting to note that the dark fringe locations of the diffraction envelope still follow the equation for the single slit diffraction, which is y sub m is equal to x times m lambda over a. So let's change it up a bit. This diffraction pattern was obtained from a setup with d is equal to 3a. Using the equation we have for determining the number of fringes within the central maximum, we get 5 fringes. This agrees with the plot, as we do see 5 fringes within the envelope of the central maximum. We're done with two slits with finite widths. Now let's move on to one more interesting pattern before we wrap things up. Let's consider the case where we have very narrow slits again, but this time we have more than 2 slits. For this example, let's have n equals 8 slits. In observing the intensity plot, notice that it is quite different from the n equals 2 case. We still have the periodic fringe pattern with the maxima, but notice that there are multiple minima, indicated by the green circles, in between the giant peaks, which we call the principal maxima. So to clarify, the principal maxima are the giant peaks. Notice that the principal maxima are considerably taller than the rest of the other peaks. The heights of the principal maxima will be dependent on the square of the number of fringes. To make sense of why this is so, let's work with the example of 8 slits. Having 8 slits means the beam will be split to 8 waves upon hitting the obstacle. We will have 8 waves interfering constructively at the positions of the principal maxima. E sub p, or the electric field of the sum of these waves, would then be 8 times E naught. And since intensity is proportional to the square of the electric field, intensity I would be 64 times the original intensity of each of the waves. In general, the intensity of the principal maxima should be n squared times the original intensity, with n being the number of slits. From the intensity plot, we observe that the number of minima between two tall peaks is 7. Generalizing the result, as we will see later, the number of minima between two principal maxima is given by n minus 1. And it should follow that the number of maxima between is just 1 less than the number of minima. I mean, you could observe yourself. Now, let's compare the 2 slit and the 8 slit examples. Notice that if n equals 2, we get our usual 2 slit interference pattern. First, we observe that the peaks have an intensity of 4I naught, so it still makes sense. And to add to that, the number of minima in between peaks is 1, which is in agreement with the n-1 equation from the previous slide. It should also make sense that there is no maxima or no more peak in between the principal maxima, because all of the peaks should be principal maxima. As expected, the n equals 8 case will have the presence of smaller peaks, as well as the principal maxima with considerably higher intensity values compared to the n equals 2 case. From what we know, we can now predict the number of narrow slits in a diffraction setup based on the intensity pattern. This example has 4 peaks in between the principal maxima, which means that there are 5 minima between them. We can then conclude that there are 6 slits in the setup, and that the brightest fringes have an intensity 36 times the original source. Before we get to the exercises, we can even level up the cases by making the slits not so narrow. For several slits with finite width, the principal maxima will just be modulated by the single slit diffraction envelope, similar to what we had a while ago. For this case, we observe that there is one peak in between the principal maxima, and this means that there are 2 minima between them, and that there are 3 slits with finite width. For this instance, we count 3 maxima in between the principal ones, which leads us to conclude that there are 5 slits with finite widths used for this diffraction pattern. Finite width because, again, it's modulated by the diffraction envelope. For this last case, we can zoom in to the space in between the principal maxima and see that there are 6 peaks in between them. There should be, or because of this, there should be 7 minima in between, and we can conclude that there are 8 finite width slits used to produce this pattern. So if you notice, the more slits that you have, the taller the principal maxima become, and the harder it is to see how many minima are there in between. So it actually becomes a lot harder for us to use this eyeball method in determining the number of slits if there are a lot of slits in the first place. With this, we achieve our final goal or objective in deducing the number of slits based on the fringes within the central maximum of diffraction patterns. Again, we're limited by the instance that we have so many slits because it becomes harder to look. I mean, we can zoom in if we have very nice instruments. Let's end this lecture with this exercise. Based on this diffraction pattern, we are asked the following questions. 1. How many slits were used to produce the pattern? 2. What phenomenon caused the imaginary red dashed line, or the envelope? 3. What phenomenon caused the pattern inside the dashed line, or the fringes? And 4. What is the wavelength of the light source used to produce the pattern? So take note that the slit width is 0.02 millimeters, so it's kind of narrow, but then it's not narrow enough to remove the envelope. And the slit to screen distance is 50 centimeters, which implies that this can be considered as far field diffraction. Now, to answer the first question, all we need to do is count the number of peaks in between the principal maxima, then add by 2. The second question has only interference or diffraction as choices, so pick wisely. And the same goes for the third question. To answer the fourth question, we have to use the equation for the distance between dark fringes, or the distance equation for the dark fringes. Y sub m is equal to mx lambda over a, because from this equation we can actually determine the wavelength, as long as we know where the dark fringes are, what the slit width is, and how far away the obstacle is from the viewing screen. So from that equation we can just isolate lambda. You may pause the video to give more time in answering the questions yourselves, as I will show the answers on the next few slides. We count 2 peaks in between principal maxima, or 3 minima, so this pattern was produced by 4 slits of finite width. We know that they have finite widths because the principal maxima are modulated by the single slit diffraction pattern. This answers the second question, as the imaginary red line is the modulating envelope caused by diffraction. This means that the pattern inside the envelope, or the fringes, are caused by interference. I mean, it makes sense. Finally, by isolating lambda and substituting the given values with m equals 1 and y equals 15, because our first set of dark fringes are located in between the middle and the edges, or you could also choose m equals 2, because the second set of minima are actually at the edges of the pictures. So that means y equals 30 if m equals 2, depending on what you choose. Regardless of what set of numbers you choose, you get lambda is equal to 600 nanometers. With this, we end the last lecture. Thank you very much for being with us in these lectures. The Physics 72 team hopes that you gained a deeper understanding of how electricity, magnetism, and light works. Good luck.